September 20th, 1941, and Flight Lieutenant Alistair Taylor sits in the cockpit of a wooden aircraft that shouldn't exist, preparing to fly deep into German-occupied France on a mission that military doctrine says is suicide. The photo reconnaissance Mosquito he's piloting carries no defensive guns, no armour plating, and no gunner to protect him from the swarms of Messerschmitt Bf-109s and Focke-Wulf FW-190s that rule the skies over Europe. What Taylor knows, what gives him the confidence to fly unarmed into the teeth of Luftwaffe-controlled airspace, is that his aircraft possesses something the Germans cannot match, something they don't yet understand, something hidden inside two Rolls-Royce engines that will revolutionise the nature of aerial warfare. Within hours, Taylor will prove that speed, not guns, can be the ultimate defence, as he outpaces three pursuing Bf-109s that chase him across France, leaving their pilots staring in disbelief as the wooden British bomber simply vanishes into the distance. The de Havilland Mosquito represents one of the most unconventional aircraft designs of World War II, conceived at a time when military thinking favoured heavily armed bombers bristling with machine gun turrets and protected by armour plates. Geoffrey de Havilland's proposal for an unarmed bomber, built almost entirely of wood, seemed absurd to Air Ministry officials who believed that defensive firepower and metal construction were essential for survival over enemy territory. The conventional wisdom held that bombers needed guns to fight their way to targets and back, that crews needed armour to protect them from enemy fire, and that modern aircraft had to be built from aluminium to achieve acceptable performance. De Havilland challenged every one of these assumptions, arguing that a streamlined wooden aircraft powered by the best engines available could simply outrun enemy fighters, making defensive armament unnecessary weight. The Air Ministry resisted the concept for years, calling it Freeman's folly and recommending the project be cancelled multiple times, convinced that no wooden bomber could survive modern aerial combat. What made de Havilland persist, despite official opposition, was his experience with innovative wooden construction dating back to the DH-88 Comet Racer of 1934, which had won the prestigious McRobertson Air Race from England to Australia, demonstrating that properly designed wooden aircraft could achieve speeds rivaling metal designs. The techniques developed for the Comet were refined in the DH-91 Albatross airliner, a graceful four-engine transport that used advanced wooden monocoque construction to achieve cruising speeds faster than the biplane fighters of the mid-1930s. These civilian projects taught de Havilland's engineers that wood, when engineered correctly using laminated plywood and balsa sandwich construction, could produce airframes lighter and more streamlined than conventional metal designs. The key was not simply building with wood, but using modern adhesives and sophisticated construction techniques to create structures as strong as metal, while weighing significantly less. By 1938, de Havilland had assembled a design team including Ron Bishop, Richard Clarkson, and C.T. Wilkins, who understood that wooden construction could produce an aircraft with the smooth surfaces and structural efficiency needed for exceptional speed. The battle to get the Mosquito into production became as important as the aircraft's eventual combat success, as skeptical officials demanded justification for every unconventional decision. Why build with wood when aluminium was the accepted standard? Because Britain would face metal shortages in wartime while wood remained plentiful, and because furniture makers and piano factories could build wooden aircraft without diverting capacity from metal aircraft production. Why eliminate defensive guns when every bomber in service carried them? Because guns, turrets, gunners, ammunition, and armour added thousands of pounds that reduced speed, and because calculations showed that a full 100 miles per hour bomber could outpace any existing fighter. Why risk a two-man crew without protection? Because the crew of a fast bomber had better survival chances than the seven-man crews of slow, heavily armed bombers that fighters could easily catch. The Air Ministry argued, delayed, and demanded modifications, including designs for gun turrets that completely negated the Mosquito's speed advantage when tested. Only the desperate need for fighters during the Battle of Britain kept the project alive, as officials grudgingly allowed development to continue while remaining convinced it would fail. The first prototype Mosquito, painted bright yellow and bearing the serial W4050, lifted off from Hatfield Aerodrome on November 25, 1940, with Geoffrey de Havilland Jr. at the controls. The flight test revealed performance that exceeded even the designer's optimistic predictions, the aircraft reaching speeds that matched or exceeded contemporary fighters while carrying a useful bomb load. When W4050 was demonstrated to Lord Beaverbrook, the Minister of Aircraft Production, in April 1941, the aircraft performed maneuvers, including a climb on one engine, that convinced skeptics the concept had merit. But the true revelation came during speed trials, when the unarmed wooden bomber outpaced a Spitfire fighter in a race, an embarrassing result for those who had dismissed the design. The combination of clean aerodynamics, lightweight wooden construction, and powerful engines produced an aircraft faster than anything the RAF had ever flown, capable of speeds approaching 400 miles per hour when most bombers struggled to reach 300 miles per hour. The secret that made the Mosquito impossible for German fighters to catch lay not just in its streamlined wooden airframe, but in the revolutionary engines that powered it. Two Rolls-Royce Merlins that represented the pinnacle of piston engine development. The Merlin engine began as a private venture in the early 1930s, designated PV-12, designed to produce more power than the successful Kestrel engine that powered Britain's biplane fighters. By 1936, when the Merlin entered production, it displaced 27 litres and produced around 1,030 horsepower, respectable but not exceptional by the standards of the day. German engines like the Daimler-Benz DB601 matched or exceeded these figures, and the Luftwaffe confidently believed their fighters possessed adequate performance to intercept any British bomber. What the Germans failed to anticipate was the Merlin's potential for development, the engine's fundamental design allowing for continuous improvement that would eventually double its power output while maintaining reliability. The key to the Merlin's evolution lay in supercharging, the process of forcing compressed air into the engine to maintain power at high altitudes where the thin air normally causes power loss. Early Merlins used single-stage, two-speed superchargers that provided good performance up to around 19,000 feet, allowing fighters like the Spitfire to compete effectively during the Battle of Britain. But in 1940, the Air Ministry requested an engine capable of high performance at 40,000 feet for high-altitude bombers, a requirement that seemed impossible with existing technology. Rolls-Royce engineer Stanley Hooker recognized that achieving this goal required a fundamental breakthrough in supercharging, leading him to design a two-stage, two-speed supercharger that would transform the Merlin from a good engine into an exceptional one. The concept involved using two compressor stages in series, with the output of the first stage feeding the second, multiplying the compression ratio and allowing the engine to maintain power at previously impossible altitudes. The introduction of 100-octane fuel from America further enhanced the Merlin's capabilities by allowing higher boost pressures without detonation, the destructive engine-killing phenomenon that occurred when fuel ignited prematurely under high compression. Early Merlins ran on 87-octane fuel and were limited to relatively modest boost pressures to prevent detonation, but 100-octane fuel's superior anti-knock properties allowed engineers to increase supercharger boost from plus 6 pounds per square inch to plus 12, and eventually to plus 18 and higher. Each increase in boost translated directly to more power, and the combination of two-stage supercharging and 100-octane fuel eventually pushed late-war Merlins past 2,000 horsepower, nearly double the power of early variants. Later in the war, 150-octane fuel became available for special applications like intercepting V-1 flying bombs, allowing even higher boost pressures and emergency power settings that could coax phenomenal performance from the Merlin for short periods. When Mosquitoes equipped with two-stage Merlin 60 series engines entered service in late 1942 and 1943, German fighter pilots found themselves chasing an aircraft that could cruise faster than their fighters could fly at maximum speed. A Mosquito bomber cruising at 25,000 feet with Merlin 61 or 63 engines could maintain 350 to 370 miles per hour, while pursuing Bf-109Gs and FW-190As struggled to reach 380 miles per hour at the same altitude. When flying flat out, the speed differential seemed small, perhaps 10 to 30 miles per hour, but this translated to a chase situation where German fighters needed significant altitude advantage or perfect positioning to have any chance of interception. By the time Luftwaffe ground controllers detected an incoming Mosquito raid and scrambled fighters, by the time those fighters climbed to altitude and positioned themselves for interception, the Mosquitoes had usually completed their bombing run and were racing for home at speeds the Germans simply could not match in a stern chase. The frustration experienced by Luftwaffe pilots attempting to intercept Mosquitoes became legendary among German fighter units, with pilots describing the humiliation of watching British bombers fly away from them despite flying their fighters at maximum throttle and boost. A Bf-109G pilot at 25,000 feet chasing a Mosquito found his fighter gradually falling behind even when flying straight and level at maximum continuous power. the gap widening slowly but inexorably as the British bomber pulled away. If the Mosquito pilot noticed the pursuit and increased speed, pushing his throttles forward and accepting higher fuel consumption, the gap opened even faster as the German fighter reached its absolute speed limit while the Mosquito still had reserve power available. German pilots reported watching Mosquitoes simply vanish into the distance, their aircraft unable to close despite being supposedly superior fighters. The experience demoralizing for young pilots who had been trained to believe German aircraft were the best in the world. The Luftwaffe tried everything to counter the Mosquito threat, establishing special units like Jagdgeschwader 25 and Jagdgeschwader 50, specifically tasked with intercepting the wooden bombers. These units received priority for the latest aircraft and equipment, but their success remained limited because the fundamental problem was not tactics or training, but performance. A Bf-109G with a single-stage supercharger simply could not capture Mosquito with two-stage Merlin engines at high altitude, regardless of pilot skill or tactical positioning. The Focke-Wulf FW-190A faced similar limitations, its BMW radial engine producing excellent power at low to medium altitudes, but losing effectiveness above 20,000 feet, where the Mosquito operated most effectively. German pilots learned to their dismay that successful interception required either catching Mosquitoes at low altitude during takeoff or landing, or having substantial altitude advantage that allowed diving attacks, where speed built up in the dive could briefly match or exceed the Mosquito's level flight speed. Hermann Göring's alleged statement about the Mosquito, though impossible to verify, perfectly captured German frustration with an aircraft they could neither catch nor shoot down. Whether Göring actually said it makes me furious when I see the Mosquito. I turn green and yellow with envy. The sentiment reflected the reality that an unarmed British bomber flew over Germany with impunity, while the vaunted Luftwaffe watched helplessly. The psychological impact of Mosquito raids proved as significant as the physical damage, each successful mission demonstrating that German air defences could not protect the Reich from determined attackers. When Mosquitoes bombed the main Berlin broadcasting station during a speech by Göring in January 1943, knocking the transmission off the air, the humiliation was complete and public. The Luftwaffe, which had terrorised Europe with its bombers, could not prevent wooden British aircraft from striking targets in broad daylight and escaping without loss. German attempts to develop equivalent aircraft failed to produce anything approaching the Mosquito's capabilities, despite intense efforts to copy the concept. The Focke-Wulf TA-154 was designed as a German Mosquito, using wooden construction and twin engines to achieve high speed, but development problems and material shortages prevented it from entering meaningful production. The Heinkel HE-219 offered better high-altitude performance than earlier German night fighters, but remained slower than the Mosquito, and suffered from chronic engine reliability problems. Even the Me-410, designed to replace the aging Me-110, could not match the Mosquito's speed at altitude, despite being a capable aircraft in other respects. The fundamental problem was that Germany never developed the equivalent of the two-stage supercharged Merlin, their DB605 engine, using single-stage supercharging that limited high-altitude performance. The introduction of jet aircraft like the Me-262 in 1944 finally gave the Luftwaffe fighters capable of catching Mosquitoes the jet speed advantage overwhelming even the wooden wonder's performance. On July 25, 1944, Lieutenant Alfred Schreiber, flying an Me-262, intercepted and severely damaged a Mosquito PR-16 over Munich, becoming the first jet pilot to damage a Mosquito in combat. The damaged aircraft managed to escape into clouds and reach its base in Italy, but the writing was on the wall. Jet aircraft represented a fundamental shift in performance that made even the Mosquito vulnerable. But Me-262s entered service too late and in too few numbers to significantly impact the Mosquito's effectiveness, and most German jets went to bomber interception duties rather than Mosquito hunting. For the vast majority of the war, from 1942 to 1945, Mosquitoes operated with near impunity against a German fighter force that lacked the performance to stop them. The late-war PR-32 reconnaissance variant represented the ultimate development of the Mosquito concept, specifically designed to counter high-altitude jet threats by flying even higher and faster than earlier versions. Fitted with extended wingspan, two-stage Merlin 113/114 engines, optimized for extreme altitude, and every possible weight reduction, the PR-32 could cruise at 42,000 feet, well above the service ceiling of the Me-262. Only 5 production PR-32s were built, but they demonstrated that even with jets entering service, proper application of piston engine technology could maintain competitive performance through careful optimization. These ultra-high-altitude Mosquitoes flew reconnaissance missions in the final months of the European War, photographing targets from heights where even jets struggled to intercept them, proving that the fundamental concept remained viable despite technological advancement. The effectiveness of the Mosquito extended beyond simply being uncatchable, as the aircraft served in remarkably diverse roles that exploited its speed and versatility. As night fighters, Mosquitoes hunted German bombers and night fighters over Europe, their speed allowing them to chase down prey that could evade slower Bristol bow fighters. The night fighter variants carried 4 20mm cannons and 4.303 machine guns along with radar, turning them into deadly interceptors that destroyed hundreds of Luftwaffe aircraft. Mosquito night fighter crews developed terror tactics like the lure, where they throttled back in bomber streams to simulate heavy bombers, then suddenly accelerated and turned on German night fighters attempting to attack them. German night fighter pilots developed Mosquito Schreck, or Mosquito Terror, living in fear of the fast British fighters that could appear from nowhere and destroy them before they could react. Fighter bomber Mosquitoes proved equally devastating, carrying bombs internally plus rockets or additional bombs externally, while retaining performance that made them nearly impossible to intercept. The FB6 variant could carry a 4,000-pound Cookie blockbuster bomb to Berlin and back, flying higher and faster than defending fighters could effectively respond. These aircraft attacked specific targets with precision that heavy bombers could not match, hitting railway yards, factories, Gestapo headquarters, and other strategic targets, while suffering minimal losses. The famous raid on the Gestapo headquarters in Oslo on September 25, 1942, saw 4 Mosquitoes fly at low level to strike the building with precision bombing, though one aircraft was shot down by FW-190s lying in wait. Despite this loss, the raid demonstrated that Mosquitoes could hit specific buildings in occupied Europe, something impossible for high-altitude heavy bombers. The anti-shipping variants of the Mosquito proved particularly deadly, when equipped with 57mm anti-tank guns or rockets, attacking German coastal convoys in Norwegian waters with devastating effectiveness. The BAMP Strike Wing, operating from Scotland, specialised in these attacks, their Mosquitoes racing in at wavetop height to rake ships with cannon fire before delivering rockets or bombs against larger vessels. The combination of speed, firepower, and the ability to escape before German fighters could respond made these attacks brutally effective, German shipping losses mounting steadily as Mosquitoes interdicted coastal traffic throughout 1944 and 1945. German sailors learned to dread the sight of Mosquitoes approaching at high speed, knowing their anti-aircraft guns had only seconds to respond before 20mm cannons shredded their ships. The Pathfinder role represented another critical contribution, with Mosquitoes leading heavy bomber raids by marking targets with incendiaries and coloured flares that guided following bombers to their objectives. Operating with the RAF Pathfinder force, Mosquito crews flew ahead of the bomber stream, identified targets using radar and visual navigation, and precisely marked aim points for the heavy bombers following behind. Their speed allowed them to reach targets first and survive in the face of concentrated defences that would devastate slower aircraft, making them ideal for this dangerous but essential mission. The accuracy of RAF bombing improved dramatically when Mosquito Pathfinders marked targets, as the fast bombers could identify and mark specific factories or facilities rather than entire city districts. The statistics demonstrate the Mosquito's exceptional effectiveness, with loss rates far below those of heavy bombers, despite operating in the same hostile airspace. Mosquito bomber missions suffered approximately 0.7% losses compared to 2.2% for heavy bombers, meaning crews had significantly better survival chances flying unarmed Mosquitoes than heavily armed Lancasters or Halifaxes. The Mosquito dropped more tonnage of bombs per aircraft lost than any other RAF bomber, demonstrating both its effectiveness and survivability. One Mosquito, designated LR503 and known as F for Freddy, flew 213 operational missions, more than any other Allied bomber in the European theatre, surviving until it crashed during a peacetime demonstration flight in May 1945, 2 days after VE Day. The wooden construction that skeptics had dismissed as a liability proved instead to be a significant advantage, allowing rapid production without consuming strategic metals needed for other aircraft. Furniture factories, piano manufacturers, and other woodworking shops could build Mosquito components without specialised aerospace manufacturing facilities, distributing production across Britain and Canada in ways that made the program resistant to bombing and resource constraints. The wood construction also provided unexpected combat advantages, with 20mm cannon rounds sometimes passing through the plywood structure without exploding, where they would have detonated against metal airframes. The wooden structure proved surprisingly damage-tolerant, with aircraft returning from missions with damage that would have downed metal aircraft, the wood's flexibility absorbing punishment that would have caused metal fatigue failures. The Mosquito's success influenced post-war aircraft design less than might be expected, as jet propulsion rendered piston-engine bombers obsolete and ended the wooden aircraft era. But the fundamental concept that speed could replace defensive armament influenced jet bomber designs like the English Electric Canberra and later aircraft that relied on performance rather than guns for survival. The idea that specialized fast bombers could perform precision attacks against specific targets, while heavy bombers area bomb cities, became standard doctrine, with aircraft increasingly designed for speed and accuracy rather than defensive firepower. The Mosquito proved that unconventional designs could succeed when fundamental principles were sound, encouraging future designers to challenge accepted wisdom and pursue innovative solutions. German failure to counter the Mosquito effectively stemmed ultimately from their inability to develop engines matching the two-stage supercharged Merlin's high-altitude performance within the timeframe when it would have mattered. By the time Germany fielded jets capable of catching Mosquitoes, the war was already lost, fuel shortages and pilot attrition rendering even capable aircraft ineffective. The DB603 and DB605 engines powering late-war German fighters offered excellent low to medium altitude performance, but could not match Merlin 600 series engines at the 25,000 to 30,000 feet altitudes, where Mosquitoes operated most effectively. German engineers understood the two-stage supercharger concept and attempted to develop equivalent systems, but material shortages, competing priorities, and the general chaos of Germany's deteriorating war situation prevented successful implementation before the war's end. The story of the Mosquito is ultimately the story of how innovative thinking, excellent engineering, and perseverance in the face of official skepticism produced one of World War II's most successful aircraft. Geoffrey de Havilland's insistence that speed could replace guns, that wood could outperform metal, and that unconventional designs deserved development despite contradicting accepted doctrine proved correct in every respect. The marriage of a lightweight wooden airframe with the war's best piston engines, specifically the two-stage supercharged Rolls-Royce Merlin, created an aircraft that German fighters simply could not catch for most of the war. That secret, hidden in the complex internals of Merlin engines with their two-stage superchargers and intercoolers, gave the Mosquito performance that rendered German air defences ineffective against determined attacks. When German pilots watched Mosquitoes disappear into the distance despite flying their fighters at maximum power, when they returned to base, frustrated and humiliated by their inability to catch wooden British bombers, they were witnessing the results of engineering excellence and innovative thinking, defeating conventional military wisdom. The Mosquito could not be caught because its engines maintained power at altitudes where German single-stage supercharged engines wheezed and struggled, because its streamlined wooden airframe produced less drag than heavier metal designs, and because British engineers had solved problems that German engineers never successfully addressed. The wooden wonder flew rings around the Luftwaffe, not through luck or chance, but through superior engineering, manifested in those two Rolls-Royce Merlin engines that hummed and roared their way across Europe, untouchable and unstoppable.